As I started saying before, we've been talking about measures of spread, right? And uh, we just got into variance. Variance for us is kind of a more in-depth calculation of spread than is the five-number summary. And I think I made this comparison before, whereas median is to well, let's say five-number summary is to median as variance is to mean, if that makes sense. Or we could say, sorry, IQR. IQR is to median as variance is to mean. Although we might want to say standard deviation instead. So here are our two formulas for variance. And you might be wondering, well, why do we have two formulas? Now, I'm going to do my best to explain this in a way that isn't, getting really in the weeds. But I want you to see that the only real difference here is with a population variance that we're measuring, we're looking at dividing by n, right? The number of items. And then if you think about it, well, our sample variance, we're dividing by n minus 1, regardless of the sample size, right? Regardless of how many items are in that list, we're dividing by n minus 1. So what does that tell you about the sample variance versus the population variance? Which one of those values will be higher? Which value would be greater, the population variance or the sample variance? What do you think? So it's either n or n minus 1. Well, will population variance be higher? Because we're dividing by a larger number, right? After this summation is completed, after we complete the summation, we are dividing by n. And n is a larger number than n minus 1, right? And as a result, we're going to have a more constrained variance with the population, right? So if you think about the variance as being kind of the average, well, it is the average distance between the mean and each data point, as we can see here. Well, distance squared, but we can see that it's an average distance. Well, we take that average distance and we divide by n, it's going to be about this big. If we divide by n minus 1, then it's going to be a little bit bigger, right? There's going to be some little bit, it's just going to be a little bit larger, right? Because n minus 1 is a smaller number than n. Now, why is this? Why is this? This is kind of an interesting, well, I think this is a really interesting thing. And it's one of those things that you learn kind of in passing when you take a stats class. Oh, well, there's this thing called Bessel's correction. And that's what we see here. For a sample variance, we apply Bessel's correction, this n minus 1. And it gets a little bit swept under the rug. Oh, okay, now we get a bunch of arrows. That's fine. We'll deal with that. It gets a little swept under the rug, or it gets simplified. We're often saying this thing of like, well, we're trying to get, for example, we're trying to get x bar to approach mu, right? In an ideal world, our x bar would approach mu. So what happens if you've got some pool of data, right? And you subsample from that pool, you subsample from that pool, and you pull out an x bar. Well, what happens next time you sample from that pool and pull out an x bar? Are these going to be the same x bar? No, they're not, actually. They're going to be different. They're likely going to be different. And, especially you have this very large pool of data, the smaller your sample, the more variability, or the more variance, actually, in your x bar. And so if we're thinking about this, if we're using this formula, which I will recopy because that is basically unreadable. If we're using this formula for population variance, we might we want to consider that mu, when we take population variance, mu is a fixed value, right? It's going to stay the same. It doesn't matter how many times we measure everything in the population, the average is going to be the same. And the variance is going to be the same, right? But if we sample from a population and we build X bar, we build this sample mean, right? Then we're actually going to get a range of sample means. And, so maybe this is big X bar, representing the the list of potential means, like maybe it's 5 and then 5.1 and then 4.8 and so on. And we might even think about, well, maybe we would average, right? Maybe we would average X bar in order to try to approach mu after a bunch of samples, right, from the population. And I think that would be a fairly legitimate way to try to approach mu. I think that's reasonable. Now, here's the kicker, though. If you are taking a variance measurement and you're getting the squared difference between each data point and X bar every time, then your variance is also going to be related to the position of X bar, right? It's going to be some distance. It's going to be some distance around. It's going to be some distance around, like, let's call this X bar sub 1. And this is going to not be consistent between samples. This width is not going to be consistent between samples. X bar is not going to be consistent between samples. And so you run into this dilemma, a little bit of a dilemma. Are you sure you're effectively capturing the variance? And so the way that we think about this as reducing bias when we apply n-1. So we can think about this as reducing bias. We'll actually talk quite a bit about bias in the second to last lecture, maybe a little bit before that of this course. But what I mean by bias here is that this population variance formula that we're seeing up here, this is pretty opinionated about where the variance lies. And we're going to soften its opinion a little bit by applying a little bit of a correction. And even this little bit of correction is going to lead us to more effectively capture the variance, the actual variance, so that the variance we're seeing doesn't, hopefully doesn't sit, the variance of the population hopefully sits inside what we're capturing as the sample variance. So I hope that's not too, too abstract. I think the main takeaway that I'm going to suggest here is that when you have a sample, you apply some correction for bias. And with this variance formula, you're going to apply Bessel's correction. In other spaces, other statistical spaces, there might be other corrections, right? And I think somebody actually alluded to that. Yeah, somebody alluded to degrees of freedom. We're not going to get too into degrees of freedom, but yeah, the idea here is that through reducing the space, reducing the freedom we have to capture the variance, we are more likely to capture, to not have sample error that eliminates the capture of the actual population variance within the sample variance that we've got. So we expand the sample variance, and we can hopefully fit the population variance inside of it. So that's a good question. How do we know that 1 is enough to reduce bias? My understanding of this is that we assume this to be true because of having done this a lot. Does that make sense? Like, this is what we apply this in statistics all the time in variance calculations. Now, here's a funny thing. There's a big argument. Well, argument's the wrong word. A really amazing discussion on Stack Overflow about the effectiveness of Bessel's correction when we're not talking about variance, when we're talking about standard deviation. Okay? So you're like, oh wait, but aren't those the same thing? Standard deviation and variance, it's just standard deviation is the square root of the variance. Well, if you think about variance as being this thing that is scaled dimensionally, it's scaled dimensionally in such a way, right? It's like, if you think about it as a big square, the variance is captured in that big square, and the population variance is captured within that bigger square, right? It's a smaller square within the bigger square. It sits somewhere in there. We don't know what it is, but we're assuming, that it probably sits in there. Experimental trials, like performing sampling processes over and over again when you have a known population mean, that's a way that you can gain surety about the effectiveness of Bessel's correction. However, there's a bit of a debate, and it's not so much of a debate, it's more of a reasonable statement that Bessel's correction isn't as relevant when you get to standard deviation. And part of that is that, well, you've collapsed your standard deviation back down into the units that you were talking about before. And the division by n versus n minus 1 isn't dramatic in the way that it can be when we're talking about variance. That's getting in the weeds. It's a really interesting post, or a series of posts. And it's the kind of thing that you never actually have to care about, unless you're really curious about it. It's a fun hole to dive down. It might change the way you think about what variance is, but for our purposes, in general, we're going to think of variance as just the average squared distance between each data point and the mean, and the standard deviation as being the average distance between each data point and the mean. So that's a kind of a long... Yes, I will post the link later. I have to track it down. I think I know where I have it, actually, because I spent a lot of... This is coming from a place where I had a misconception, okay, about what we were trying to do with sample variance. And I read through this whole thing, and I'm like, oh, wow, I've been lying to myself about what the variance is, since I learned about variance ages and ages ago, right? And that happens I think that just happens in life all the time, where you're like, oh, wow, this thing that I've just tacitly believed is not true. And I think those are really, those moments, solidify a different type of understanding. I think those are some of the best learning moments. But yeah, I'll definitely share that article, share that forum post, because I think it's really fun. It's also, like I said, it's esoteric, and you do not need to know it for what we're doing. The takeaway, again, we're going to think about Bessel's correction as kind of expanding the space so that the variance that we measure is more likely to capture the population variance. So from here, I think the next thing I'm going to have you do is code the variance function. So, yep, that is exactly what I'm going to have you do. And there are some prior functions that you're going to find helpful, right? The mean function, you're going to need that. Really just that. So let me paste in the mean function as well. Let's see, I should have it up here. Just in case you don't have it handy. And what I'd like you to title your function, the name of your function, let's just call it variance. So def variance, and I think I put 4 minutes on here, but I think in the past I've found that people don't usually get this coded within 4 minutes. And part of that is that you should have, okay, so you're going to pass in a list, right? But you should also have a flag, right? Where the flag is differentiating between whether or not it's a population or sample, right? So you could do, what I usually do is sample gets true. And I know you can't see that, but let's... So that's what I'm suggesting as your function header. And yeah, you're just implementing this in code. I'll put 5 minutes on, and if we need to extend by 2 minutes, we can do that. Okay. All right, go for it. Let me know if you want 2 more minutes, and I can do that. Just give me a thumbs up if you do. All right, I'm going to start coding through this. I saw one of the solutions, the first solution that was posted. I think in your second return, in your else statement, did you mean to do the length of the list minus sample? I notice you have minus trim there, but I don't see trim defined anywhere. But I like that you threw everything into a comprehension. This is actually a function you could write as a one-liner, but I'm not going to do that. I think sometimes I'll entertain that because it's fun and it's good code too. But in this case, I just want to break it out, make it as simple as possible. So I think the place where some people get hung up on this is in the interpretation of the sigma here. This is just a summation. And if you think about what a summation is, it implies an accumulator, right? It applies a plus gets kind of system. So the first thing we're going to need, a thing we're going to need is the mean. And I can just call mean of the list. And then I'm just going to make an accumulator. So I'll just set a total. And then for each item in the list, I'm going to accumulate into this. And I'm going to save the division by n or n minus 1 until the end, okay? So for each item in the list, the total is just going to get the difference between each item and the mean, right? And we square that. Okay. So notice I could say if sample. So if sample is true, right? Just if sample. We can return that total divided by the length of the list minus 1. Otherwise, we would just return the total minus the total over the length of the list. So remember that a Boolean true is mathematically equivalent to 1 in Python, and that creates a little convenience here. So we could actually do this. We could say the total over the length of the list minus sample. And then we can simplify our code a little bit. So so you can see right now that you could collapse this. Those of you who know how to write comprehensions, you could collapse this into a single line function if you want. I'm not necessarily recommending that, but you can totally do that. So, the only thing about doing that though, notice that if you do that, if you collapse this into a single line function, you would be calling the mean of the list function n times, right? You would be calling it for every item in the list, because you'd be getting that difference every time. So there is some utility. This function is slightly better computationally because you're not going to do that. You already have the mean packed into a variable that you can reuse. So, just throwing that out there. But good on you if you did write a comprehension, and definitely try to get this into a one-liner if you find that kind of thing fun. So let's talk standard deviation. I said this before, that the variance, right, is this larger dimensional space. It's an out of scale. It's a squared scale of the units that we're looking at, and because of that, it's not easy to interpret. Whereas if we take the square root of the variance, that gives us the measure of spread within the units of the item that's measured. So very often we will convert this to standard deviation. How do we do that? Well, that's easy enough to do, right? That's like, in fact, I'm not even going to do this as a breakout. I'm just going to show you, right? Sigma squared, here's sigma, we just take the square root of this, right? So if we want to do that, there's a couple ways to do that. The first way, let's see, I'll call this, I'll just call it standard deviation. STDEV, standard deviation, pass in a list, we keep the same sample flag, and all we need to do here is return the variance on that list, pass in sample, and then we can raise that to the 1/2 power. It's slightly better in Python if you import the square root function, but it's such a minor difference in computation speed that I wouldn't even worry about it. But if you wanted to do that, you could write it like this: from math import sqrt, and you would just take that sqrt function and wrap it around your call to variance. So you could do that. Either way is completely valid, and what I'll do right now, I'll paste both of these in because you're going to apply them. There's Slack. In the last breakout for these slides. So make sure you copy that, unless you want to do stuff by hand, which I don't encourage, but feel free. So This we already saw this data before, and I'll paste this in. So this is going to be the data that we're using, and let me put the prompt here as well. Okay. So an issue of a recent magazine reported the following home sale amounts for a sample of homes in Alameda, all of which were sold in the previous month. And these are in scales of thousands of dollars. So one of the houses sold for $590,000, and you can figure everything out from there. So find the variance of the homes sold in April, find the standard deviation of the homes sold in April, and if we exclude the values we considered to be outliers, do you think the variance will increase or decrease? And it says here, check your answer by making the calculation. But I actually don't worry about checking your answer. I want to hear what you think. I want you to think about that, and don't verify it necessarily with the calculation. We'll just talk about it. So I'm going to put 5 minutes on the timer, and yeah. See where you end up with this. All right. See, a number of you have gotten to the correct solution here. I'm going to, I'm going to do this in Python. And yeah, I'll just go through each of these. So the first thing we need to do is find the variance, right? So with that, well, I always find this helpful. I'm just gonna print out the sorted version of the house prices, which I think where do I have those? Oh, good, I have them there still. And I can print the mean of the house prices as well. So I'm gonna do that, just so that we can kind of look at these together. So here's the mean of the house prices, and then let's print the sample variance of these prices, and that'll just be the variance of house prices. Sample gets true. I don't actually have to put sample gets true there. That's the default value. So I still do it though, because for reasons I explained in a previous lecture, I think it's just nice for people when they're reading your code to see that. Okay, so let's also look at the standard deviation. We'll want to see that. And standard deviation, house prices, sample true. All right, let's take a look at that first. Oh, let's do. All right. So we can see that we have this mean that is all the way out here, right? We've got a mean somewhere right out here. Our variance is this, 64,141,000. And I think that, is clearly hard to interpret. Well, what does that mean? This should say standard deviation. But when we think about the standard deviation, well, that looks pretty reasonable, right? Yeah, maybe the average value between each data point and the mean is around 253. I could see that. If we're at about 620 and we've got something here, we've got this larger value out here that's going to, drag open our standard deviation, then it makes sense because most of the rest of these values are within roughly 100, right? Like this whole set of values are, all of those are within 100 of our mean. And so, the expansion of the standard deviation seems clearly related to this 350, 408, and 1285. So that kind of leads us to the next part of this. Well, what happens when we remove outliers? Well, you remove outliers, that tends to constrain the standard deviation or the variance, right? It pulls it in. So let's take a look at what that is. Let's remove outliers. So I'm just going to do this, removing outliers. And then I'm just going to put this outliers removed is going to get, well, we have a function to do this, right? So I'll just call that function the remove outliers function on the house prices. And now we can, we can just look at I'll just grab all of this and we'll swap in everything that we need to swap in. So house prices, no outliers. We'll replace everything here. Okay. So when we look at this, that's pretty dramatically different from our that should say standard deviation. This looks quite a bit different, doesn't it? We've got just a severe reduction in the variance and of course the standard deviation, and we can see that we can see fairly easily here that if our mean is at 594, 46 could be easily the average distance between 594 and each data point. So we'll wrap up the summary stats at this point. Why don't we, before we jump into sets, or kind of this intro to sets and set theory, let's take a 6-minute break. That way we're just coming back into that. And I'll see you all back here in 6 minutes. If you have any questions, just post them in the Slack, and I'll either answer them right when we come back, or I'll answer them over Slack if they're answerable over Slack. Okay, I'll see you all back here in a couple minutes. Okay, so we're going to start looking at set theory. And this lecture is going to be, or the materials we cover in set theory are going to be, not super deep. We're going to stay fairly shallow with it. It's not a shallow topic. In fact, it exists in, across so many different maths. If you're studying discrete math, you're going to have set theory in it. If you're studying probability theory, you're going to have set theory. Set theory is under so many things that we do. That said, we won't need, we're going to just borrow some things from it. And we're going to focus on those things and leave like the greater topic kind of for your own studies. So what we're going to, kind of establish here initially is what we think, how we think about something called a random experiment, and the sample space of outcomes related to a random experiment, and then, this word events, right, which is synonymous with outcome, right? An event can be considered an outcome. And then we're going to talk about a couple of specific set operations, unions, intersections, and complement in particular. We're going to expand on some of that in the next lecture. We're going to think about unions, intersections, and complement in light of what we call axioms of probability or axioms of set theory, depending on where you learn it, or foundations of logic is another way. Notice those all seem like disparate things, and they're actually all the same thing. I could also throw in there, abstract circuit design is actually the same math that we're going to be looking at here. So, with that said, let's think about what it means for something to be a random experiment. So, there are a few takes we could have on this, but kind of the foundation that I want to throw out there when we're thinking about a random experiment. It's some phenomenon that has a quantifiable outcome or a discernible individuated outcome, right? Something that we can say, this is the outcome, right? That could look like a lot of things. If the phenomenon, let's say the phenomenon is the height of trees, and we're measuring the height of trees, we might consider a random experiment to be, okay, well, pick any tree and measure the height, right? And maybe that tree is, like 10 meters or something like that. Maybe another tree that you measure let's say of the same species, is 7.3 meters, right? That's only two measurements, but the random experiment, the results of the results of the random experiment, the outcomes of the random experiment, the events of the random experiment, are going to be of the sort that we can have some range of outcomes, right? And in this case, we're measuring, but there is a finite number of trees in this forest, and let's assume that each tree is its unique measurement. We're going to compose a set from that, a set of the measurements, right? If we exhaustively measure every tree. Something that might be a little bit, quicker to think about is rolling a die. And we are often going to talk about rolling dice and, choosing cards. And we're going to talk about these as phenomena, right? Pulling marbles out of a bag. This is the pastime of statisticians is, they're experts at, pulling marbles out of bags and pulling numbered balls out of, boxes and things like that. Things that, we don't do in our everyday world, but we think about a lot in the world of statistics. So if we're thinking about rolling a die, well, there's a certain set of outcomes, right? And that's a way that we talk about it. There's a set of outcomes. And that set of outcomes could be, 1, 2, 3, 4, 5, 6, if it's a 6-sided die. So, at that point, we can start, we can even start thinking about probability, right? We can ask the question, well, what's the probability that you get a 1 or a 2? Okay? And we might even start thinking about this as, there is a subset of the set D that we're going to call A, and that subset is composed of the items 1 and 2, or the outcomes 1 and 2. So, we can even go so far as to say, well, A, and this is a funny symbol, A is an element of D. We're not going to, worry too much about, that symbology, but what we are going to think about is we're going to get to the point of thinking about probability as being, a subset of outcomes divided by by the containing set of outcomes, the superset, or containing set, the universal set. There's a bunch of words like this. So in this case, this would be, you might see it like this: the length of A over the length of D. And this would simply be 2 out of 6, right? Or 1/3. So here's something about random experiments. Is it a random experiment if we have an outcome that is guaranteed, right? Like, let's say the experiment is flipping a coin that has 2 heads, and the outcomes we're thinking about in terms of, well, are you going to get a heads or not? Well, if it's guaranteed that you're going to get heads from the flip of a 2-headed coin, it's not really a random experiment, is it? If you differentiate those heads and think about them as 2 different outcomes, sure. That would be, we could think about that as a random experiment. But random experiments are, they require that there be more than one potential outcome. If an outcome is not in a set, like let's say a coin flip, right, where we have heads and tails. Let's say there's this other outcome, arm, okay, this is actually an impossible outcome in terms of the experiment of flipping a coin. Getting arm is just not going to happen. So those are indicators that, well, if something's impossible or certain, it's probably not a random experiment. So how do we define a set? I'm just going to pull this slide up, and then we'll talk about it a little bit more. A set, this is not the most satisfying definition, I think, but we can call a set a well-defined collection of objects. All right, well-defined. Part of what makes it well-defined is that our objects are unique. The set is defined, in essence, by the objects it contains. And we don't have duplicate objects in there. We don't have duplicate outcomes in there, duplicate events in there. We have only one of each, right? And so when we're talking about, even when we're talking about something like a bag of 3 different colors of marble, for example, let's say we've got some bag, and we've got red marbles and blue marbles and green marbles. And these are pretty much, when we talk about bags of marbles, we always say red, green, and blue. I don't know. It's like 30% of the stats problems out there. Now, even though we have multiple marbles in there, we have multiple blue marbles, multiple red marbles. If we're talking about the outcome as being a color of marble, right? then our set is only going to be red, blue, and green, right? These are all the potential outcomes for marbles. Now, that doesn't tell us the number of red marbles. It doesn't tell us, because maybe there's 70 red marbles and 30 blue marbles and 50 green marbles. It doesn't say that these are equally likely outcomes. It just says that these are the potential outcomes, red, blue, and green. So if we're thinking about all the possible outcomes of an experiment, right? Let's go back to that six-sided die. So six-sided die. Our potential outcomes, of course, are 1, 2, 3, 4, 5, and 6. We call this the sample space. Okay. So the sample space for the outcomes of one die roll, where all we're considering is the count of the dots, which we call pips, the count of the dots on a die. This is the entirety of the sample space, 1, 2, 3, 4, 5, or 6. We call this sample space. We often represent this with a capital S. So we might represent it, though, with a capital U. And that just means the universal set. It basically means the same thing. And you might see this as a capital omega. I'm not going to do that. I'm probably going to use capital S pretty much all the time in this case. And that's there's a reason I'm going to do that. I think it's just easier to think about, and we're going to get into how set theory moves us toward probability. So there is a set data type in Python, right? And you've learned a little bit about it. Now, one thing across languages, across programming languages, that we use sets for is this thing called the list set trick. And people often refer to it that way. I don't know if that's an official name. I'm sure there's something more official than that. But let's think about what it means to be a set. Well, in Python and in set theory, sets have unique objects. So if you have a list of items, right, and there are duplicates in that list, you can remove duplicates by turning that list into a set and then turning it back into a list. All right, so let me just demonstrate this. Let's have a list of, well, I don't know, a list of furniture, chair, table. How about, oh gosh, stove? Is that a piece of furniture? I guess you can sit on a stove. And let's put another table in there. Okay, so the list set trick, you're just going to cast the list to a set and then cast it back to a list. And that will remove duplicates. So let's just see that. So list dupes removed, and let's go ahead and run that. So Python sets. So notice we get table, stove, chair. Also notice that these are not in order anymore, right? Like what we're seeing here is not in order. And the implication here is that sets don't have order. They don't guarantee order in Python, but even in set theory, a set is not an ordered entity, right? It doesn't matter where an element exists in the set. It's just in there or it's not, right? So even as Python, I'm not saying that's why Python gives us, sets in no particular order. But we don't actually guarantee order in Python sets. So what happens if you want to maintain the order of appearance of various items, right? So let's, I'm going to demonstrate this. I actually have this as a breakout, but I think I'm just going to demo this because it's maybe not entirely obvious at first, but yeah. So let me show you the prompt, and if you want to code this while I'm coding it, if it feels within your range, do that. But I also want to just talk through this and get us to a solution to sort of like give a foil to the list set trick. So I'm going to write this function called dedupe in order, okay? And it's going to take in a list, and it's going to remove duplicates from that list, but it's going to maintain the order of the items as they're seen. And the reason I'm doing this is to kind of differentiate the algorithm from another algorithm, right? The list set trick we can think of as an algorithm, but there's a thing it doesn't do for us. It doesn't keep things in order of appearance. And if we need order of appearance to be maintained, then we need to write a different function. So I'm going to do a simple collector here, just called deduped. And then for each element in the list, so I'll just say for each element in the list, if the element is not already in deduped, then we can append it to deduped, right? So deduped.append, and let's append the element. And then we can just return deduped. So let's see how this functions on that same list. And do this. Okay. So now, notice chair, table, stove, and we get rid of this last table, right? Because it's a duplicate. We don't add it in. So this is two approaches to solve almost the same problem, but actually a slightly different problem. And it's those subtleties that come up quite a bit when you're programming. You might be working on Code Wars, doing some kind of prompt on Code Wars, and you get to an answer, and it's not the wrong answer, but it's not actually the totally correct answer. And because of that, it's failing tests. And so you need to account for these other cases, right? These other subtly different cases. And in this case, right, the algorithm is very different. Instead of just casting twice, we're actually building we're taking an accumulator approach. Okay. This is kind of all to say that sets don't allow duplicates, right? And we can use that to our advantage on the Python level in a lot of cases. So we already talked about sample space, so I'm not going to. And I talked about subsets. Let me just say. Let me say a little bit more about subsets. Let's go back to our idea of a die, okay? And with this, again, our sample space is one. I'm not going to draw all these out, but 1 or 2 or 3, 4, 5, or 6, right? So we can create subspaces, subsets of S, right? And we can just give them a name, and we can define a rule for the items that populate them. So if we say that A is the subset where the outcome, where the outcome here is showing a number greater than 3. Okay, well, that would be 4, 5, and 6, right? So we can see that A is composed of 4, 5, and 6, and A is also an element of S. So if we say B is there's an even number of pips or dots. So let's say an even number of pips. Well, what is that? That is going to be it's going to be 2, 4, or 6. And we can see again that B is a subset of S. B is contained in S. And then C, well, C could be let's just say it's exactly, C is the exact event 5. Okay. So we can see, of course, that C is an element of S. All elements in C are elements in S. C is a subset of S, but it only has one element. So we can then notice that C is also a subset of A, right? C is also a subset of A. 5 is an element of this, and there are no other items. And we can also see that B and A have some elements in common, right? They have the element 6 in common. So we can start thinking about this interrelationship. Notice that when we talk about sets, when we give them names, it's usually a capital letter, right? So thus capital A, B, or C in this case. Okay. And here's something about set theory that you may or may not like. I think I'm a little on the fence about it. I don't really think easily in Venn diagrams, but in set theory, we are constantly representing things in the form of Venn diagrams. And I'm going to do this, for the next couple lectures. I'll probably do this quite a bit. So let's say, I'll just give you the basic form of this. We have some sample space S, and we usually represent it like this, right? Where S is this big box. And S contains events, we'll just do A and B. So we've got A here, which is not exactly a circle, but let's try to make a circle. That's good enough. So this is A, and this is B. And we can start thinking about the relationship between A and B and their relationships with the containing set S, our sample space S. So there are operations, what we call operations, that we can perform. And the performance of those operations gives us some subset that is either A or B or neither of them or something else, okay? Now, we'll talk about 4 set operations today. And I'm going to show you kind of code. I'm not going to code this stuff out necessarily because it can be pretty time consuming, and I think it's more important to get the idea of what's happening here. But I just want to show you, we've got unions, intersections, set difference, and complement. That's what we're going to be talking about. Those are the 4 operations that we're concerned with. So let's start off with set union, and it's convenient. I've already got this up here. So the union, we often equate this with an OR statement in logical operations. Okay? So what this means for us is any element that is in A or in B is, gives us the composition of A union, and it's this sort of, U without a tail, A union B. So what does that look like visually, or how do we think about that visually? Well, it's everything in A, everything that's in both A and B, and everything else in B. Something to notice here is that the stuff that's in this intersection is has the potential to be duplicated, right? But we don't accept duplicates in a set. So, when we're doing this, we don't want to add duplicates in. Okay. So, how do we think about this in... let's take this a step further, actually. Let's add a set C before we get too far. Let's say there's this set C. We can also union C to this, right? And then notice we're just going to kind of put this in here too. So you can see that there are going to be many items potentially duplicated here, but we don't allow duplicates. Again, we don't allow duplicates. So let's think about this. Well, you know what? I'm going to have you code this. And I'm going to give you a little bit to start with, because I think this is good algorithm practice for very basic algorithms. So why don't we... I'm going to have you code the set function. And the way this will look, the set function, the union function. You're going to call union on a list, and you are going to return the union of two lists. So let me give you a couple lists to work with. In fact, let me give you 3 lists to work with. So let's think about these as sets, all right? So I'm going to call this one A, and B and C, but we're not going to use the set data type in Python. We're going to use lists. And the reason we're going to use lists is to get you used to the manipulation of lists and, getting the outcome that we're actually looking for. So let's do, let's do animals. The set A has a bat and a cat and a dog and a weasel and a dolphin and a zebra. How about that? And let's say set B has a dog, a weasel, a dolphin, and a zebra, and then also has a squirrel and, a vole. How about a vole? And let's say set C has a dolphin, zebra, a squirrel, and a vole, and then how about a manatee and a sloth? Okay. So when we're thinking about the union for 2 lists, how would you compose that? Well, I think you would look at everything that's in A and see it and put that into a container, right? Put that into a collector. And then anything that's in B that isn't already in that container, you're going to put that in there too. So let me give you this set of data. So you've got sets A, B, and C. I'm going to give you 4 minutes to code the union function, and then we'll look at how to rebuild this to accommodate more than 2 sets. Oh my gosh, I realized that I have led you all a little bit astray. I actually meant to make those all lists. So, not sets. And because I want you to take a procedural approach to solving this and not a set approach. So, I think this is probably going to be a freebie, and I'm probably just going to code through this and show you what I mean. Sorry for pasting in the wrong data. I will paste in the corrected data. And actually, I'm going to put 2 more minutes on. Yeah. Okay, so let's do this. All right, so notice that I said code this for 2 lists, not necessarily all 3. We want to be able to pass either, any 2 of these in. So the first thing that I'm going to do is make a union. So I'll call this set union, and I'm just going to use this as a collector, and I'm going to take that first list 1, and I'm just going to copy that. I'm going to copy all the items in. And then from there, and this is kind of longhand. You could do this in a different way, but I think this is fine. So for each item in list 2, if that item is not in the set union, then we want to put it in there, right? And we can just say set union dot append the item. And when that's all said and done, we can return set union. And now we can check this out. We can look at it in relation to our sets that we have here, which are really lists, but we're going to think about them like sets, but we're going to write procedural code because they're lists. So let's do union of A and B. Let's print that. And let's print the union of B and C. Okay, so the union of A and B, we can see is, bat, cat, dog, weasel, dolphin, zebra. Notice that it gets all of those in order from set A. And then we get, we get squirrel and vole because the rest of these are duplicates, right? Dog, weasel, dolphin, zebra are all duplicates. And then the other one we're looking at here is dog, weasel, dolphin, zebra, squirrel, vole. And then the only two things in here in set C that aren't in B are manatee and sloth. So if we were to do A and C, that union would, be all of these items through zebra, and then squirrel, vole, manatee, sloth, right? We can see that, but we just don't have duplicates. So what about taking the union of an arbitrary number of sets? Well, we're going to use that as an excuse to explore another concept in Python. I'm not sure if Clark has talked about this, but there's this thing that we call star args. So there's star args, and then there's quargs is another thing that we're not going to talk about really. But star args is it's a parameter you can define, and you can pass in an arbitrary number of things, and that'll be treated like a tuple within the function. So let's make an example, just a quick star args example. And let's just do that. So this is just a quick aside on star args, because this is going to be handy for us when we look at how to do the union of multiple sets. Okay, so I'm just going to write something really boneheaded. So I'm going to define a function called star args, and I'm going to declare this thing called star args. Now, I could call this anything. I could call this star stuff. It doesn't matter. I could call it star. Args here is just a convention. It's just what we tend to call it. And the first thing, I just want to show you this. Well, what is the type of args? Well, let's call this, and we'll pass in, we'll pass in a list, and then we'll also pass in a string, and we'll pass in a number, 32.7, and see what that gets us. Well, we can see that the type of this is tuple. So what it's done here is it's taken this argument, or these three things that we passed in. Now, notice up here, we didn't create three parameters. We didn't create three containers to hold those values. What we did is we created a wildcard that can take as many items as we want to pass in. So we can pass in these three items, and they get turned into a tuple. All right. However, if I make this into a tuple, then it's a little bit weird, right? In this case, I'm making a tuple, and I'm just passing in a tuple as its own entity. So that might package a little differently. So I'm going to not wrap that in a tuple. I'm going to keep them as independent arguments that are passed in. So there's our type. And just to show you that this works, show you how to traverse this, we can say for each item in args, args is the same as this, right? The star here is just a wildcard that we throw on the front to say it's going to be of an arbitrary length when we call the function. For each of those items, we can do anything to those things, right? Here I'm going to print this. Also notice that you can't modify items in args because it is a tuple, right? So we couldn't do something like, you know, args sub 0 gets not a list anymore. We don't want to do this, and it'll break if we do. Okay, so notice here I'm just printing stuff. I'm not returning anything. I'm going to explicitly say return none there just to remind everybody that when you don't explicitly return something, you're actually returning none. Okay, so we can see here that we operate on this just like it's a list. And I've just printed these items as if they're just items in a list. I mean, they're items in a tuple, so, you know, same ability to traverse it using a for loop. All right, so we can, I'm going to do the first example of a union for multiple sets. So I'm going to code through this breakout. I usually do this, and then I have you write the next one where we use the star args. So I'm going to write this function union of multiple sets, and I'm going to declare star args. And maybe instead of calling it args here, I'll call it multiple sets. I can follow the same pattern as I did before, right? I could say set union is going to get, I'm just going to make it empty this time. I'm not going to make a copy. And I'm going to say for each list in multiple sets, I can just say for each item in the list, if the item is not in the set union, then we can append it to the set union. So notice what I'm doing here. The first item, A, let's say it's A in multiple sets, well, I'm just going to look at each item in that list, and if it's not already in the set union, I'm going to append it. And then I'm going to look at B, and anything that's in B that isn't already in set union is going to be appended. And then I look at C. So I could define 5 more sets and just throw all of these in there and build the union of as many sets as I need to with this approach. So let me just test that really quick. I'll print the set union of A, B, or C, and let's see what we get. We get an error. Set union is not defined. Oh, that's because I called it union of multiple sets. I'm returning the set union up there. Okay. Okay, bat, cat, dog, weasel, dolphin, zebra, squirrel, vole, manatee, sloth. I'm pretty sure that's what we're looking at, right? Bat, cat, dog, weasel, dolphin, zebra, squirrel, vole, manatee, sloth. So that's working as we'd expect it. Now we could simplify this a little bit, okay? So I could say something to the effect of, I don't know, I could say set union gets multiple sets sub 0, right? And if the length of multiple sets is greater than 1, then I can get the union, right? I can update the set union as the union of set union with, oh, sorry. There needs to be a for loop in here. So I can say for, let's see, for index in range and length of, actually, let's do this, for item in multiple sets. And we'll skip the first one and continue on from there. The set union is going to be updated as the union between itself and the next item. So why don't I call this, instead of item, next set. Just to be semantically clear. So let's see if that works. This way we are, we're utilizing the prior function. And we get the same outcome, right? So it's a different algorithm, but it's getting us the same thing. And I'm not suggesting that you write functions that depend on other functions necessarily. Just understand that you can do that, right? We already wrote a union function. And if you find this to be simpler to understand, where we're just taking the union of the set that we're composing with another set, well, we can do this this way, or we can do this with a nested loop, with a nested for loop. This is not a nested for loop, right? Well, it is. It is technically, because we're calling out to this other function, and there's a for loop in that function. But in this case, we've actually simplified how we think about the algorithm. Okay. So let's think about the next construct, the next operation. And my suspicion is that we'll probably finish with this. We'll probably get partway through this and then call it, because we only have about 15 minutes left. But let's talk about the intersection. So the way that we think about intersection is that when we compose, say, set A with set B, and why don't I just draw this? Let's make our sample space S. All right, here's S. Then we're going to make A and B. So here's A. Here's B. Oh. There we go. Oh, it's still terrible, but that's okay. Let me just mark that. The way that we talk about, or the way that we write the union of, the intersection of sets A and B is with a symbol that's sort of opposite of the union symbol. It's this upside down U with no tail, right? So A intersect B. And all this is what is shared between A and B? Well, it's any elements here, right? This is the intersection of A and B. And we often think about the logical equivalent here of intersection as being the AND operation. Okay? We'll get more into that tomorrow. Or sorry, tomorrow? I think tomorrow, yeah. So let's make set C in here just to point this out. Well, here's C. Now, what this means, if we intersect A, B, and C, well, this stuff that's right here is no longer valid in here. So we have to get rid of that. And we just have only the elements that they all share as the intersection. So thinking about this, you're going to write a function. You're going to write the intersection function for 2 lists, okay? Don't worry about making it accommodate 3 lists. Although if you want, feel free to try to make it accommodate an arbitrary number of lists using star args. Although that's going to be a separate breakout. So the function name is going to be just intersection, right? So let me just delineate this. So def intersection, and you're going to pass in, say, list 1 and list 2. right? And you can use that same data that I shared before to test this. So yeah, 3 minutes on this. The reason being, this is a slight adaptation from the prior function. Okay, starting the timer now. Okay, so let's see about adapting this from our prior function. So I'll go up here and I'm just going to snag this union really quick. And I'm going to have to change a few things, right? So this isn't really the set union, is it? It's going to be, I'm going to call this the set intersect. And in this case, I don't really need to make a copy anymore. And instead I'm going to make an empty list. And then for each item in list 1, instead of list 2, I'm just going to say list 1. If the item is not in the set intersect, and also if the item is in list 2, then we can say set intersect dot append the item. And then, oh, I don't know why I didn't update this last one, but intersect. So let's see about the intersections of A, B, and C. Okay. So let's do set intersect of A with B. You can print that. Actually, why don't I do this? I will call this A underscore B, about A and B. I'll print that. And then I'm going to also print the set intersect of that A and B with C. Let's see what that is, what that does. Set intersect is not defined because I called it intersection. That's the same exact error I made before. Huh. Okay. So the intersection between A and B gives us dog, weasel, dolphin, zebra. And I think we can just see that, right? These share dog, weasel, dolphin, zebra. We can see it very clearly because of the way that I built these. And then we can also see that dolphin and zebra is the only thing that C shares with both of those. And so ultimately we end up with the intersect of A, B, and C as dolphin and zebra. Okay, so I'm going to go ahead and code the intersection for multiple sets, just to do it, since we have about 5 minutes. And I think this idea, I used to spend a lot more time on it, and I think there are other things I've been spending more time on. Star args are cool, but you might not need them right now. I just don't want you to be surprised when you see them later. So I'm going to just define this kind of the same way I defined the intersection for, the union for multiple things. And I'll call this, again, I think I called it multiple sets before. And this is fairly straightforward, right? I can say, well, there's going to be a collector called the set intersect, which is an empty list. Now, there's something that may not seem immediately obvious here. If we want to check one list against the other lists, it means that we have to have a list in there, right? It means, well, we need to have something that has more than one item. And so, otherwise, if we try to intersect something essentially with itself, it's just going to return itself. Or in our case, oh wow, zoom. Okay, so the first thing I'm going to check, I'm just going to check the length of args. I'm going to make sure that we have more than one thing coming in. And if we do have more than one thing coming in, and the length of the initial set is greater than 0, right? Because if that initial set, the what I'm going to call args, well, multiple sets sub 0, which is actually this should be greater than 1, and multiple sets and the length of that initial set, imagine A, if A has nothing in it, well, we can't really do an effective intersection. So I'm just going to take care of that. All right, so once we deal with that condition, then I'm going to check every item in args sub 0. Sorry, multiple sets sub 0. Keep calling it args. And I'm going to just have a quick Boolean in here. Is this item a member of all the items in the other sets? And so I'm going to say, well, let's assume it is first. And then I'm going to say for each other set, right, in multiple sets, starting at the first item, the first indexed item, right, which is the second item, through to all the rest of them. For every one of those, if the item is not in every one of those other sets, right? It has to be in every one. And if it's not, right, if it's not in there, I'm going to raise a flag that says false, and there's no reason to check any further than that, and I can just break at that point. And then if that item passes all those tests, then I can say set intersect dot append item. And let me make sure. Okay, we'll go all the way to there. So return the set intersect. And the assumption here is if we pass in set A, and we only pass in set A, that we're trying to intersect with the null set, or with an empty set. And of course, as we'll see next time, the intersection of a set with nothing is, well, nothing. So let's call this on A, B, and C, and discover if there are any errors in here. So pass in A, B, and C, and this should just be dolphin and zebra if it's performing correctly. Yeah, so that's working. Something you might think about is remember how I rewrote this union of multiple sets to use the union function. You might think about rewriting this. See if you can rewrite this at some point so it uses the intersection function above. And you should be able to get rid of, you should have a slightly less verbose function at the end of it that is dependent on the intersection function. Okay, so next time what we'll get into is, we're going to wrap up this slide deck. There's only a few more slides on it. We're going to look at set difference and set complement, both of which are things we're going to utilize a lot, and we're going to think about complement kind of in a lot of spaces in terms of probability, in terms of how we think of a sample space. So I want to give that its fair time. We'll do that in our next lecture, and yeah, I think that's it for today. Yep. Thanks so much. Feel free to sign off. If you have questions, stay on. I'm going to go ahead and stop recording right now.